Hi, everyone. Thanks for waking up. uh, so my name is Parth. I work on a bunch of efforts in platform security related to firmware. Um, Things I've worked on include firmware integrity, verification, and firmware management, so patching, settings, BIOS, passwords, etc. Today, we'll talk about Intel AMT and how to use and abuse it. As a warning, I'm a Linux user, which means the presentation has a natural leaning towards it. So if there's something Windows-specific that I missed, please feel free to tell me. Here's what I wanted to do when I started working on this presentation. I wanted to explore the best possible attack using legitimate AMT functionality. So the keyword there is legitimate AMT functionality. Once I had explored the attack, I wanted to then present on my story that attempt, all the challenges, roadblocks, etc., that I encountered during a practical attempt. Hopefully showcase the complexities involved for an attacker, and you can decide at the end how realistic this is for your situation, given the various nuances that I'll cover. I also wanted to present all available options for people to detect, mitigate, or prevent such attacks. Finally, I wanted to present a story of how to do forensics if an attack like this does happen. The reason I've put in the effort to put together this presentation is to share what I've learned. I've been looking at AMT on and off over a couple of years, and I think a lot of the implications are not too clear, despite being documented. So by doing this presentation, I want to save other people the time and effort that I spent. But before we jump into those three things, let's develop a shared understanding of AMT first. So in this section, we'll cover what is Intel AMT, what are AMT's core features, what are the requirements for using AMT, provisioning AMT. We'll look at AMT in the news lately, and then open source AMT tools that exist. So what is AMT? AMT is designed to be an always available solution, even when there is no OS or even when the machine is off. It's meant to be available as long as network and power are connected. It's implemented within the management engine, the ME. The ME runs on the chipset itself, which is separate from the main processor. Talking about the ME is a separate presentation. Since AMT is part of the ME, you can imagine AMT as effectively being hard-coded into the motherboard. Hopefully you can see why I called it the ghost in the machine. Anyway, let's take a look at the core features of AMT. AMT allows you to do pretty much everything as if you were physically present at the machine. So you can do remote power management, off, on, restart, etc. You can boot off a network image presented as a CD-ROM or a floppy drive to the system. So the ME will emulate an IDE CD-ROM drive to the system. And from the OS perspective, it's as if it's physically plugged in. Using the remote floppy, we can exfil data. So I actually tested mounting a large floppy drive, which is 1 GB big, over the network, and you can exfil data over it. KVM, you can use KVM to observe or take control. As if you were physically present again. This requires the display to be connected to integrated GPU, Intel integrated GPU, which most laptops have. Serial over LAN is, again, similar to CD-ROM. A serial port is emulated by the ME and presented to the system. This has many use cases. One of the core usages for managing BIOSes, since most BIOSes have a feature that allows redirecting the screen to serial. So you can reboot, redirect BIOS output to serial, and now over LAN, you can manage the BIOS. And one of the most interesting features is the client-initiated remote access, or CIRA. So one use case is a user is off-site, and they can initiate remote help at boot time. It'll work with a broken OS or even if there is no OS. Again, all you need is power and network. The idea for this is for AMT to connect to an admin server when someone's off-premise and create a tunnel for support personnel to come back through. So this way you can bypass NAT or anything else that you may have. CIRA tunnel can also be set up to auto-dial at specified times for checking in centrally. This is for checking in new settings, or this can be to check to make sure the laptop has not been marked as stolen. So hopefully that gives you a good idea of some of the core capabilities AMT has. Next, what are the requirements for having AMT? There are 3 steps for being able to use AMT remotely. Manufacturer decision, BIOS settings, whether it's on or off in the BIOS, and the actual AMT setup, which is called provisioning. Because of manufacturer decision, AMT is not present in most consumer devices. From my understanding, the ME module, the AMT module, cost extra for manufacturers and licensing fees. But business desktops and laptops usually always come with AMT as a feature add, and it's usually enabled in the BIOS by default. It's enabled but not provisioned, so there are two different things that you have to keep in mind. Some of the more beefier spec consumer devices also have AMT. So provisioning. So what does provisioned mean here? It means to activate any of the AMT interfaces for usage. To do that, you have to set a bunch of bare minimal settings, and the process of setting those things is called provisioning. What the bare minimum settings are depends on how you provision. The method determines what the bare minimum settings are. And we'll have a look at that next. Generally speaking, there are 4 broad ways you can provision AMT for usage. And there are 2 provisioning modes available once the provisioning is done. So the provisioning mode ACM, or admin control mode, or CCM, or client control mode, is meant to reflect the level of trust required to complete the setup process. Note that all of these 4 options intermingle and can be used in combination with each other. So try not to think of them as distinct options. They can even be used after the provisioning is done to set other settings. So number 1, local agent on OS. This requires you to have AMT software installed and running as root or admin. Easy if you have Windows, there's Windows tools out there. If you have Linux, you write your own custom tool. Again, it needs to have admin privileges in order to talk to the ME interface, which is how you'd communicate with the Intel ME. This method, local agent, will put you in client controlled mode, which will give you limited AMT functionality. You can carry out additional steps to transition to admin control mode, which is when you have full functionality, which is when you can use Sierra, for example. Second option is remote. This requires pre-setup at factory or via USB, using the third option. In this case, for the remote option, what AMT will do is it will send hello packets over the AMT LAN for up to 6 hours after first power on. After that, it will turn off. It will stop sending packets. The time period is configurable up to a maximum of 24 hours only. So it's not too bad. And the responding server that responds to the hello packets must present a certificate that's pre-trusted by the AMT. And that pre-trusted certificate is it's configurable either at factory or again via USB. The third option is setting up via USB. You place a setup.bin file on a FAT32 USB, and you can configure AMT at boot time. Finally, provisioning can be done physically via the BIOS MEBX menu. This is a 10 easy to follow steps that we carry out about 30 seconds. As I mentioned before, these methods can be used to set further settings even after provisioning is technically complete. So the line between provisioning and configuration is a bit blurry. To be exact, provisioning can be considered complete as soon as AMT exposes any of its 2 interfaces for use. So AMT has 2 interfaces, local and remote. As soon as any of them are exposed for API calls, provisioning is done. And it usually happens as soon as you change the default password, which is admin. Okay, that's enough on provisioning. AMT in the news. Some of you probably have seen this already, but a quick mention on a couple of the items. So first is Intel SA75, which is escalation of privilege vulnerability. In short, it was HTTP digest auth could be bypassed with a null or empty response once an AMT interface is exposed. So this allowed anyone to get in and have admin access over AMT without actually knowing the password. For this, to exploit this, AMT obviously had to be provisioned, and the attacker had to be physically on the same network. So that were the 2 mitigating factors. Patch is available, so if you haven't patched, maybe you want to. But if you're not using AMT, then maybe you're not impacted. Second thing that was in the news this year was Platinum Group. They were seen hiding communication from the OS by using serial over LAN. This way, you could bypass any network monitoring you had on the OS. And that's how they managed to do some exfiltration of data. It's quite a unique usage. There's probably more things to come here. Quick notes on the tools that are available. Everything is in one convenient central place, meshcommander.com. I use both of these tools, Mesh Commander and Mesh Central 2. So you'll see them referenced during the slides. It's all open source. It's most of the development is actually done by Intel employees, but they've open sourced the actual code. All right. Let's go back to looking for the best practical attack. Now we know a little bit about AMT. When I started this exercise, this is what I wanted to achieve. Obviously, when I started, I didn't know this was really possible. It seemed likely from the documentation I had read. So my goal was to A, control AMT, B, maintain persistent access, and C, remain stealthy in the process. So let's quickly cover what to do afterwards. I didn't carry out these steps I'm about to show you, as there's nothing AMT specific here, but I'm laying these out so people can see an end-to-end picture here. So once I have AMT control, what can you do as an attacker? What is it that AMT allows you to do? So as a standard attacker, you can use AMT to restart the machine, boot to your own disk, replace the unencrypted boot parts on the hard drive to hijack the disk encryption password for next time around. You can come back a few days later, reboot, and then use the encryption password to replace binaries on disk, and now you have root on the machine. Anyone with repeated physical access to your machine can do this today. The difference with AMT is I think you only need one-off physical access. The reason I put down easy to hard in the difficulty is because the success here depends on if you have secure boot and or trusted boot being used. Even if some or all those are being used, how the BIOS is protected also contributes. We'll touch on it again when I talk about mitigations later on. As a sophisticated attacker, you can, again, reboot to your own disk, but this time insert an SMM backdoor into Flash, or system management mode backdoor. This is not a universal attack, and most machines also severely lock down writing to the BIOS region, even if you have root of the machine. So that's complicate your life. That's why I put it in the hard category. But if you're a nation-state actor, maybe this is something you have in your arsenal. Did I miss a scenario here? Maybe you can think of another attack vector. If you can, let me know at the end. I'm curious to hear your thoughts. Okay. Back to exploring our aim of getting AMT control. So what are our options for provisioning AMT on a target machine? So we can either subvert the supply chain. The complexity here is high. You can say medium if you think it's easier. So the likely attacker here would be someone who's highly resourced or casting a wide net or targeting someone specifically. Provisioning method can be anything. You have physical access to the machine. This includes things like unattended packages, so that's why it could be medium. If you think, depending on where you live, maybe it's common to leave laptops being posted unattended for hours while outside, for example, outside of your apartment. Second option for provisioning is you have root or admin on the machine already. The provisioning method is local agent and OS. The complexity is high for a well-secured OS, or medium if you think it's easy to get root on a box. Another reason for high is because, as I mentioned earlier, when you provision via local agent, you only get client control mode, which doesn't allow you full control of AMT. The likely attacker here is, again, sophisticated, someone who's looking for long-term persistence, because if you already have root on the box, what do you want AMT for? I feel that both of these are quite hard to carry out and unlikely for different reasons. What's most likely is the final one, physical access. So here the complexity is low. All you need is a USB, plug it in, walk away. Likely attacker, someone who's either targeting you specifically or opportunistic attack. Could be evil maid type attack or shipment interception. The provisioning method here is either USB or the BIOS menu. For me, physical access seemed the easiest way to proceed, so that's what I ended up choosing. Let's tweak our goals to be explicit. Since easiest attack vector requires physical access, I've excluded desktops. Laptops travel, get left unattended, so this seems unrealistic. I'm assuming if you went out to dinner last night, you've left your laptop in your room, right? I've written Lenovo X1 Carbon here, but I've also tested on a couple of other laptops. That's just a sample laptop I used. Okay, so let's lay out our assumptions so far. Firstly, obviously the machine we target has to have AMT support. Next, Intel AMT should not have been provisioned already. Some BIOSes allow unprovisioning from the BIOS menu without knowing the AMT password, but others don't. But the laptop we're targeting here, Lenovo, does not allow it, for example. So it's important for our target laptop that the AMT is not provisioned. Thirdly, the MEBX password, which is also known as the ME password, should still be the Intel default, which is admin. This is usually the case. If you buy in large enough quantities, then you can ask the manufacturer to set a different password at shipment time. But unless you're going to use AMT, why would you do this? Finally, either AMT should already be enabled or a BIOS password is not set, so we can enable it ourselves. Okay, so here's an ideal attack scenario. Look for an opportunity or create a distraction. Then, since we'd like to spend as little time as needed to provision and set up AMT, we'll use USB to auto-provision AMT and set up AMT to auto-start a CRA connection to my command and control server, and done. That's what the documentation says should be easily doable. Does that seem plausible in 60 seconds? Maybe 30 seconds. So this is the ideal. Do this, walk away. Unfortunately, there were some problems, and that's what makes it a fun story. So here's what I found out trying to do it. USB provisioning file can be easily created using the open source software I mentioned earlier, Mesh Commander. It's painless. It worked even when it seemed it shouldn't have worked. So for example, it worked even when there was a BIOS password set. It worked even after I removed the USB from the boot priority order. So I tried all the options to disable USB in the BIOS, and it just kept working. But the downside was only a very limited number of settings can be set via USB. It doesn't allow me to set all the AMT settings. And unfortunately, CRA is not one of those settings. I can set a remote provisioning server, in which case AMT will make a call to the remote provisioning server asking for further configuration, and then the remote provisioning server can push down CRA settings, but I can't set up CRA settings directly. So that's a complication. What options do we have to proceed? Option A, as I mentioned, I can set a provisioning server and then use that to push the CRA settings that I wanted to push. Firstly, the provisioning server will have to be on the same network, so I can't do it. It can't be on my command and control server outside the network that I'm in. And this is because the external network won't be able to respond to the hello packets because of NAT, for example, which is what we want to solve by having CRA, so we have a chicken and egg problem. So we'll need to bring along a Raspberry Pi or something similar, running a provisioning server which can plug into the network port, and then we can still do it. It's just a bit more effort. And secondly, there is no easy-to-use Linux software for the provisioning server. Writing my own provisioning server seemed like too much work, not something I wanted to get into. So the open source tooling is being actively developed, and this is one of the things they will add at some point. So if I wait long enough, it'll show up. So second option was manual setup through LAN. The cost here is increased attack timing. So what happens in this case is I would, once the AMT is configured via USB, some of the basic settings are done, I would connect the laptop's LAN to my own network, again, a Raspberry Pi or something, and then since AMT now is fully provisioned, I have access to the full API, which means now I can make API calls to AMT to set up CRA that way. So either I have a script or, so it adds about 30 seconds to the attack if I use a pre-scripted API, API calls using a script. If I do it via a nice GUI, then it takes about 3 more minutes. And that's the way I ended up doing it because I'm lazy. And there's a video of the Mesh Central developer on YouTube showing you exactly how to do this. The video is titled Mesh Central 2 Intel AMT CRA. That's it. So if you want to walk through how to do option B, it's online. In both cases, though, you either need built-in LAN into the laptop or a native LAN adapter. So let's update our assumption slide. So for our attack, the machine needs to have either built-in LAN or native LAN adapter, which AMT will use to listen to by default. USB LAN adapters will not work since AMT doesn't listen to them by default. So for the Carbon X1 that I used for my testing, it doesn't have a built-in LAN, but it does have a custom LAN adapter, which is available, which does a pass-through, and which is seen as native LAN by the system. And what I found is, generally speaking, most business laptops either have built-in LAN or have what this X1 has, which is a special adapter, which is presented as built-in LAN to the system. So this seems like an acceptable assumption to me still, because business laptops still have this. So attack steps. Preparation, set up USB, set up command and control server, write AMT serial script, bring LAN adapter and a cable. And execution itself is reboot, plug in USB, press yes, plug in LAN cable and adapter, trigger the script, and then done. And then check the command and control server. Hopefully it shows up. Results. Here we're connected via Sierra to this laptop. It's configured to dial out to my server every 10 seconds there, periodic connection, and maintain a tunnel forever as soon as the connection is established. If the internet drops out, it'll keep trying for 10 seconds, and as soon as it's established, it'll stay connected. Mesh Central 2 here takes care of the rest. I even configured Sierra to dial out over Wi-Fi in case LAN is down. In this screenshot, I'm connected via Sierra tunnel, which is established over Wi-Fi. I also tested KVM over the Sierra tunnel. This was tested over LAN only. It should work over Wi-Fi as long as an OS agent or a Wi-Fi driver isn't loaded. So this is the interesting part. So AMT is configured to hand back control of the Wi-Fi radios to the OS as soon as a Wi-Fi driver is loaded. In the normal use case, the Wi-Fi driver is meant to pass the messages between AMT and OS, or an OS agent is meant to take over the CRR or KVM connection. I didn't try this as we assumed that we didn't have that level of access, so we don't have admin yet. But as an attacker, once you have AMT control, we kind of assume that now you have admin. Other functionality I didn't test, mostly because it's not implemented in Mesh Central 2 yet. I tested that independently. So remote mounting and booting disks. As I mentioned, I tested mounting the floppy drive. I also tested booting of a remote Debian. It works as featured. Nothing unexpected there. So AMT seems to be most useful when the machine is connected to LAN. Some people do use laptop docks, but it's not significant or reliable. As mentioned before, Wi-Fi control is handed back to the OS when the Wi-Fi driver loads. But the driver loaded may be the correct one for AMT. So there are specific drivers written for AMT usage, which automatically takes care of handling the messages. And I'm not sure if it's included by default in Windows or not. For Linux, we know that's not true. Also, to use Wi-Fi, the profiles must be loaded into AMT. AMT supports up to 16 Wi-Fi profiles. So in this case now, the attacker needs to know which of the local APs are likely to be available. He needs to know, and the attacker needs to know the credentials, passwords, or certificates, whatever's being used. So if you're surrounded by well-known APs wherever you work or at home, and the creds are well-known, then maybe this becomes more of a concern for you. The standard attack that I mentioned earlier still works. So an attacker who boots their own OS simply shouldn't load their Wi-Fi driver. If they don't load the Wi-Fi driver, then AMT Sierra will continue working because the radio controls will not be handed back. Hopefully you've got a fair idea of what's involved for using AMT for attack. Despite the Wi-Fi limitations, it definitely seems something to be worried about since it has such powerful, legitimate features. This concludes the attacker focus of the presentation. Next, what can us defenders do? Let's look at options we have for detection, mitigation, and prevention. First up, how do we detect when an attacker is abusing the ghost in the machine? Network-based. So look for well-known network ports. Remote configuration and provisioning request always calls out to TCP 997.9971. Just hard-coded TLS is well documented. The source ports for AMT-initiated packets, which includes CIRA connections that are outgoing, always cycle between TCP 16992 and TCP 16995. So this, again, is hard-coded. These are reserved specifically for the AMT usage. And the source ports usage makes sense because otherwise the OS would intercept. CIRA connections can be mutual TLS, but they're always at least TLS. So this makes it harder from network detection point of view. So the way mutual TLS is set up with CIRA is a server public keys inserted into AMT at setup time, so either at factory via USB and marked as trusted. And then AMT will generate a certificate, private key of which can never be exported, containing a specific string which the server, when it presents its certificate, must present as well. And this is how AMT will authenticate it's talking to the correct server. It knows that it's meant to be talking to the server only. Whenever CIRA is during CIRA, all inbound network ports are closed. So if you probe any machine with AMT provisioned and CIRA enabled, then you will not get any response. But if CIRA is not enabled, then AMT will respond at 16992 usually. So that's still a possible venue for scanning your network. If that's not good enough, if you're worried about CIRA connections, then the only other option you have is an OS agent. So you have an OS agent running as root, which talks to the ME interface to query the state of the AMT. If an attacker already controls the OS when the agent is running, then the MEI status registers can be faked with a bit of effort. So the tool needs to be deployed prior to OS compromise. So you can just be included in your normal build, for example. For Windows, this is not too hard because there is an existing tool you can just deploy. For Linux, a bit of effort is required. You kind of have to write a custom tool. As an aside, with the network-based stuff, while I was working on this, I did network captures of the CIRA sessions using a physical network tap that was sitting between the Lenovo and the wall LAN adapter, and it confirmed MTLS, mutual TLS. User detection. So, it's worth mentioning as a reminder that there's always a possibility of detection by user. So if, as an attacker, you boot a custom OS, it'll show up on the screen. Windows Tray app called IMSS will also show a pop-up if it's installed. This is sometimes installed by default by manufacturers. Obviously, if you're an enterprise and rolling your custom OS, you may have removed it. And finally, KVM displays an animated sprite on the screen. So it's animated, it blinks, and it moves. Cannot be disabled. So if someone is doing KVM and the user is present, the user hopefully will have some alarm bells going off. And also, if you're in client control mode, which is what you end up in if you provision from the host OS, from with an agent on the OS, then the KVM cannot be initiated until a user says yes. They get a dialog, and the user actually has to consent. Only in admin control mode can you disable the consent, but you still can't disable the sprite. So what are your mitigation options? So ideal, you have a verified boot chain, which means you can't replace bootloader with a malicious bootloader because the machine would no longer boot and unlock the encrypted disk. For Windows, secure boot is supported and BitLocker is available. So making sure it's correctly set up is a different problem, especially for an enterprise. For example, if BIOS parsers don't exist on laptops, then an attacker can, if they have physical access, which is our assumption, they can disable secure boot by going to the BIOS menu because there's no password to stop them from doing so. But if you have BitLocker set up with TPM-backed keys, then the user will be notified and the hard drive won't be unlocked automatically if you've tampered with any of the boot parts. So that's why I have Windows as achievable. Linux is a different story. And Macs, well, they don't have any of those concepts. Existing mitigations that exist currently is that not many people use LAN with laptops regularly, so it makes the attack slightly harder. Wi-Fi is limiting, as I said. The attacker has to know the APs, they have to know the credentials to get into them, and they have to insert it into AMT. The biggest mitigation is enterprises that allow internet access through a proxy only. There's no way from within your enterprise to get out to the internet without going through a proxy, then Sierra will not work. It's designed not to work with proxies. And as mentioned before, KVM will display a sprite, so that's a detection mitigation, I guess. Finally, how can you prevent such attacks altogether? Well, obviously, don't buy machines with AMT. Unfortunately, this is not really an option if you want anything that has high specifications, because it comes with AMT by default, and it's usually on by default in the BIOS. It's just not provisioned. The other option is you control AMT, so you get in there for yourself first, so you provision it, and then since you have provisioned it with an admin password, the attacker can't get in. This means that you're actually voluntarily signing up to enterprise rollout of AMT and management of it as well, which is maybe not something you want to get into. And the third and final option is you disable AMT within the BIOS and set up BIOS passwords so an attacker cannot enable it again. If you want to do this again, the difficulty here is for an enterprise. So imagine a fleet with multiple vendors, multiple OSs, and each vendor giving you a separate tool in order to control the BIOS settings. This is where the complexity comes in for enterprise rollout. But the problem with the BIOS password is that you don't want the same one for your whole fleet, otherwise effectiveness is drastically reduced. If it gets out once, an attacker already knows it. Ex-employee, for example. So unique BIOS passwords per machine is another management nightmare. So you have two problems now in order to disable AMT effectively for an enterprise. You need to be able to control BIOS settings from the OS, and you need to be able to set unique passwords per machine so that it actually has some mitigating effect. Password management feels like the 90s now. So in short, the two real options you have is either take control yourself or disable AMT and set a BIOS password. Finally, obviously, we need to make sure the BIOS actually respects the disable choice of AMT. So there is a Lenovo advisory from last year where Lenovo, even when AMT was set as disabled in the BIOS, still provisioned via USB. It just worked. So it doesn't matter if you had a password, doesn't matter. Anyway, hopefully, if you're a defender, you have some options available, you have some ideas, you can take a look. What if you're an incident responder? So this is the last part of my presentation. Someone takes over AMT on your machine, excuse me, and you somehow detect it. What options do you have? So de-chipping is an option because it's physically on a chip, but it's not scalable in terms of cost or time. The AMT API, without knowing the admin password, is useless. Of course, you can use the auth bypass vulnerability I mentioned earlier, but you should have patched that, right? So this actually happened. So a plugin I had written for internal network scans detected a provisioned AMT on the Google internal network during a regular scan. We didn't know the admin password, and the owner said he had no idea what this was. So panic, time to investigate. First up, we did some due diligence. A colleague of mine checked network logs for everyone who ever talked to any of the AMT ports on that machine. The answer was all internal ports and IPs. Nothing looked suspicious. I collected a BIOS dump using GR. So GR, which is GRR, is Google's incident response tool. It's open source. It has the last year, a year before, we added the functionality to be able to collect BIOSes using this. So I collected a BIOS dump for that particular Linux machine, matched it against the official BIOS from the vendor by pulling both of them apart using UFI extract. It's actually the project that I've actually worked on a lot last year. The comparison results were good. There was no modification that I could find. Everything looked legit. Nothing to worry about. I reached out to the AMT, Intel AMT team to ask how I could do forensics. I had a quick meeting and found out that no one had asked them about this before. I was pointed to a Windows tool which can be run to generate a status report of AMT. I asked about Linux since the machine in question was Linux, and I didn't want to boot up Linux. So I didn't want to boot up Windows just to run this Windows tool. They don't have a Linux team anymore, so they have nothing for Linux. So what I wanted, a Linux tool, which allowed me to dump full AMT audit log. So AMT, again, one of these legitimate functionalities is it has an audit log, and it logs everything you do with it. The log can be cleared by an admin, but that leaves a log entry itself. It'll say the log has been cleared. So if I can get to the audit log, it should tell me something about what has happened with AMT. What I actually got, unfortunately, was a Windows tool. I ran the Windows tool, and the output just told me that AMT is provisioned. And I was like, yes, I figured that much out. So I dug a bit more. I spent time poking at the Windows tool. I learned that it was calling get local system account via the ME interface. The ME interface, the MEI, is exposed via driver, which interfaces with the management engine. And the get local system account tries to get the password for an inbuilt user called $OSAdmin. So this is an AMT user, which is built in and has limited access. So that call retrieves the password for that user. That password is randomly generated at each boot. That account cannot be disabled, and the password cannot be controlled. But the $OSAdmin account doesn't have anywhere near the full access that the admin user has. So I set about replicating this idea to Linux. The ME interface driver is already in mainline Linux, so didn't have to do any work there. It's exposed as /dev/MEI if you want to have a look. Need IOCTL to talk to it. I wrote some quick Python to retrieve credentials. Note, doing IOCTL using Python, not a good idea. It was not fun. But I was getting desperate for a solution. I got the passwords, but the credentials didn't work. And what I learned there was the limitation of $OSAdmin account is it only works locally. So using the creds to call the AMT API over the network, as I was doing to this Linux machine that was sitting somewhere in the world, didn't work. Here is an interesting problem now, because the OS cannot talk to the AMT ports directly. The way the AMT works and the ME works is whenever network packets are received on the physical LAN, the ME grabs them off the physical LAN before the OS sees it. This is how you communicate with the ME or the AMT. But if the OS tries to, if you send the packets via loopback address to the same port, the OS never touches physical hardware, which means the ME never sees it, which means you can't talk to the ME through loopback address. So what next? I found out that I needed LMS. Sorry, I've got 5 minutes. I'm going to try and speed up a bit. So LMS exposes all AMT network ports to localhost. The software is available for Windows, but obviously not for Linux. The The Linux version was open sourced about 4 or 5 years ago, but not maintained. Thankfully, I was able to use it with a few tweaks. So, retrieving the AMT audit log. I built LMS for Linux with some minor fixes. The patch for getting it to build is in the repository being open sourced. The bugs are pretty minor. I succeeded in dumping the full AMT audit log using the creds through the LMS. The audit log records are base 64 encoded. Decoded string was mostly garbage. I said mostly because I could see some readable ASCII words. There was no documentation, no public documentation on what to do with the base 64 string. So this is where Google failed me quite miserably. I think I spent ultimately 4 days trying to figure out how to decode this. In desperation, I went to Intel AMT SDK, which is about 250 megs zipped. It's meant to contain the sample code for all API calls to AMT. So I was hoping for hints on parsing audit log records. This is where I wasted 4 days going through all sorts of code trying to figure out what the struct is. Finally, I got the structs. It was very painful. But here are the findings. This is the actual screenshot of the audit log from that machine. AMT was set up in 2015 January, but we received the machine in September 2016. So something with factory mistake or interception. But the audit logs matched the IP logs we've already observed externally. So nothing seemed suspicious. The audit logs matched perfectly. Nothing had been done, no Sierra connections, no remote KVM, nothing had been initiated. It still looked fine. So at this point, nearly closed the investigation, except as a last-ditch thing, I sent an email to the machine vendor asking for history, saying, okay, where has this machine been? Because the AMT was provisioned about a year before we received it. What's going on? So 26 emails, 2 weeks. What I learned was the machine was actually received in 2013. Our inventory was wrong. And the machine started its life as part of the Linux test lab. It was not part of standard inventory. It was used for testing Linux builds. And the test lab used AMT for automation. And in September 2016, which is what we have in the inventories, when the machine was decommissioned from the lab because they no longer needed the machine and added to the general pool, it ended up on a user's machine, and that's when we detected it on our internal scans. So lesson was inventory is hard. And next time I have this problem, I will not waste 3 weeks. I will track down the history first. Anyway, that concludes my story. Some things I've learned since through Intel lately. You can have a read. I've run out of time, so I'll just go to the slides where you can get the slides and you have a look yourself. You can ask me questions afterwards.
We still have room for one question. Yeah.
So whenever the attacker provisions the machine and it starts the heartbeat tunnel to the Sierra server, so is it true that from the client OS you cannot see these heartbeat packets?
No, you cannot see them. You cannot see them even if you're on the network. All you see is encrypted packets.
Yeah, but from the client OS you don't see the packets at all.
No, because
okay.
As I mentioned, AMT grabs packets directly off the adapter and puts directly on the adapter, bypasses the OS completely. That's, again, it's designed that way because if the OS is broken, how is it meant to work?
Okay, thanks.